Thank you, Renzo. And I'd like to thank the organizers both for the opportunity to speak and also for the effort that they put into this conference. I was here at the first one 2 years ago, and I'm really excited to be back again with you this week. To start off, happy Pride from my family. This is me and my husband Bill and our son Ben, who's 5 years old and just finishing kindergarten. And the project I'll be talking about today is joint work with Joshua Jackson, who's a postdoc at Sheffield. And first I'm going to tell you a little bit about geometric invariant theory, or GIT. And that will allow us to interpret the main problem I'm speaking about today as a quadratic programming problem. I'll show you some examples and tell you our main conjecture, and then give you the answer for cusps. All right, so to start off with, geometric invariant theory. GIT is a general technique in algebraic geometry, and it's when you want to form the quotient of a scheme by the action of an algebraic group. And so this is something that's especially useful when you're constructing moduli spaces. And so the setup here is that we'll have some space X in a projective space, which is a projective scheme. And I will have a reductive group, and there's no harm in thinking today that we're just working with SL n+1, acting on Pn by some representation. And then, if you were trying to form a quotient in algebraic geometry, here is one natural candidate for doing so. You could look at the ring of G invariant polynomials and then take proj of that. Now, there are some issues that come up though when you're working with GIT quotients that you don't see when you're working with quotients in other categories in mathematics, like in topology or differential geometry. And so here's the first one that I want to mention. In general, you expect that a quotient map in a category that you're working in should be a morphism in that category. And that's not always true in algebraic geometry. And it's easy to see what the problem could be. If all of your G invariant polynomials vanish at a point, that point is a base point for this morphism. Okay, so we get around that by making a definition. All right, so the semi-stable points for this group action are going to be all the points where you have some non-vanishing invariant section. Okay, and then you get a nice morphism from the semi-stable locus down to the quotient. Now, based on that description, you might think that all of the attention should be on the semi-stable locus because that's where you actually get a morphism. But it turns out that it's interesting and important to study the complement of the semi-stable locus as well, and Mumford named that the unstable locus. So in this talk, unstable is the opposite of semi-stable. So let me just mention a few facts about the unstable locus. Kempf proved a conjecture of Mumford that when something is not semi-stable, there is a worst destabilizing one-parameter subgroup lambda that is somehow the most responsible for what goes wrong. In a technical sense, he proved there's actually some function that you can cook up and that your worst one-parameter subgroup is a maximizer for that function. It turns out lambda is actually also not unique, but all of the worst one-parameter subgroups are related to each other in a nice way. And so I'll use the article A even though it's not unique. And so now I want to just quickly mention a few applications of nothing that we can get to today for this particular project, but some of the things we have in mind for the future. You can use the worst one-parameter subgroup to get a stratification of the unstable locus, and this goes back to work of Hesselink and Ness with applications by Kirwan to computing cohomology of quotients, and then also in Daniel Havren-Leissner's newer theory of beyond GIT, these ideas become important again. And so, like I said, you use this stratification by the worst one-parameter subgroup when you're trying to compute cohomology of quotients, and also in these more modern approaches, you can try to interpret these strata as moduli spaces in their own right. So those are all things we'd like to get to in the future, but to do it, or we'd like to have an idea first of what the worst one parameter subgroups are in some important examples. Okay, so what are some interesting examples? And so let me just start with this old theorem due to Mumford and Giesger. If you take connected one-dimensional scheme of arithmetic genus G at least 2, and suppose that its degree in projective space is at least 9 times G minus 1, if you have something that's semi-stable either for the Chow GIT problem or for the asymptotic Hilbert GIT problem, then it's either smooth or any singularities are nodes. Okay, so in all high degrees, the only semi-stable stuff are smooth objects and nodal curves. Okay, and this is specific to curves, not surfaces or anything higher dimensional. Okay, so now we have a rich supply of unstable GIT examples, namely any singularity worse than a node. So we've known for 40 or more years that all of these singularities are unstable in sufficiently high degree embeddings. And so it's natural to ask, well, what is Kemp's worst one parameter subgroup for any other singularity? And surprisingly, despite the passage of time since these results first appeared, these answers are unknown. And so Daniel Halpern and Leisner asked this question, and Josh Jackson had been thinking about it a little bit. And so we set to work, can we answer this question for some curved singularities? Yeah. Oh, yeah. So here, embed your curve in projective space Pn, just SLN plus 1. Yeah. Okay, so a wide open problem. Uh-oh. All right, so to start, we made a simplifying assumption. So you could ask a question about any singular curve at all, and we decided to start with something a little bit easier. So let's assume that we have a rational curve with one unibranch singularity. In this case, you get a semigroup that's naturally associated to the singular points. And so that's how we're going to phrase the rest of our discussion, all in terms of this semigroup of this singularity. And just because I'll use these words a little bit in my talk, this semigroup is the complement of a finite set in the natural numbers. And the number of gaps you get is the arithmetic genus of the singularity. And the first number after the last gap is called the conductor. And so if you hear me speak about the conductor, it's where you get everything from that point on in the natural numbers in your semigroup. Yeah.
The group involved, sure, it's SLN plus 1.
Yep.
But that group may not stabilize C. So does that matter? I think I just have a question about that.
But for all sufficiently high degrees by Mumford and Giesger's theorem, this will be unstable.
You use the wrong. I didn't mean to say stable.
Oh, okay.
It's a technical term you use before.
Yeah.
The group SLN plus 1,
Mm-hmm.
and they carry the curve onto a completely different curve. And so in your first slide, it was like, how do we push it up X by G?
Mm-hmm. X is the Chow variety here. Capital X is the Chow variety, and little x and x is a curve.
Oh, dear. X. Okay.
Sorry.
X is Chow D, and C is now a point there.
Sorry, okay. Yes, okay, so let's start with good examples. All right, so I need a singularity that's worse than a node. So how about the simplest cusps you can think of, y squared equals x cubed. All right, so you can start off obviously in P2, and so we can start with a nice parameterization using these powers of t, or if you want to see it projectively, there it is. So simple cusp is going to have arithmetic genus 1. And then the point is that you could embed this in higher dimensional projective spaces as well, just by using more sections. Okay, so here it is in P3, or we can continue this pattern, and we could get a rational curve in Pn for any capital N that has one singular point that's given by a simple cusp y squared equals x cubed. And we know by Mumford and Giesecke's work that for all sufficiently high degrees n, this thing is going to be unstable. Sorry, and in fact we know classically this is unstable in every degree, or for every n greater than or equal to 2. But what is the worst one-parameter subgroup? Okay, so just in our general setting, I'm going to work with these sort of similar curves that we're going to call monomial curves. So these are given by sort of the projective closure of images of maps that look like this. So you fix a semigroup, you choose some large degree n, you chop off your semigroup at that number, and you use the elements in your semigroup to give you the exponents for this map. Okay, and so you're going to get some rational curve with some interesting singularity given by that semigroup. And the reason that we chose this class of examples is because we can apply a theorem by Kapranov, Sternfels, and Zelevinsky. We have a curve with a GM action, and so you could think of it as a non-normal toric variety. And in this case, the Chow state polytope is equal to what's called the secondary polytope of the thing that you use to define your toric variety. And for us, here's what that means. This Hilbert-Mumph function, the thing that helps you compute the worst one-parameter subgroup, has a really natural interpretation in pictures. It's the area under the lower convex hull of the points that you get by graphing the gamma i's. So those are the numbers in your semigroup, along with the weights that you're going to try to assign to a one-parameter subgroup. And then we can say further, there's some explicit vector that you can cook up just in terms of your semigroup gamma, and also an explicit polyhedral cone W, which you can write either inequalities or rays just using the elements in your semigroup gamma, so that the worst one-parameter subgroup is just given by the closest point between this polyhedral cone and this vector outside. Okay, and so the point of all this is, in this particular class of problems, everything we want to know is given by answering some completely explicit problem in convex geometry. And it's all governed by the combinatorics of the semigroup gamma. And so with that interpretation of things, we're able to use software to compute the worst parameter subgroup and see examples for the first time in 50 years. So let's take a look. What happens for a simple cusp? So again, my semigroup, we have just one gap. You leave out 1, and as n increases, you get all the numbers from 0 through n except the number 1. And so I'm going to show you some pictures for what happens for different values of capital N. So when n is capital 10, the worst one-parameter subgroup, when you graph its weights, you just get a straight line. If you go to n equals 20, you get something that has 1 corner, 2 line segments. Take n a little larger, now you get 3 line segments, and you get 2 corners at consecutive integer x values. Take n a little larger still, we're back to 1 corner. And finally, when you take n equals 160, it's hard to see in this picture, but there's actually 2 corners. They're almost right on top of each other. They're at consecutive integers, but you just get 3 line segments like this. Okay, and so if you check this carefully for every value of capital N, you would naturally get the following conjecture that for one range of values of n, you get a straight line, then you develop 1 corner, then you get 2 corners, then 1 corner goes away, and then you get a 2nd corner again at the end, and that appears to be the answer for all sufficiently large values of n.
It went a little too fast. A one-parameter
Yeah.
subgroup, I think
I think of it as a homomorphism from GM into your group. But in our case, once you know the weights, that tells you sort of the exponents by which your GM is acting.
Oh,
So it's
you're
t goes to t to some power.
So this polygon
Mm-hmm.
is the way of describing a conjugacy class of homomorphisms in GM into SL plus 1.
Yes.
Its weights.
Yeah. Mm-hmm. Okay. Now, so in general, I don't know the answer for all singularities, but I do know that we can prove the description you're seeing on this slide for a simple cusp y squared equals x cubed. That's true. So this is one of the examples where we know this is the right answer. Let me show you one more picture. So this is a different semigroup now. So this is the semigroup generated by the integers 4 and 9. And if you go to n greater than or equal to, I believe, 46, you see the following picture. It'll have 5 corners total at the 7th, 8th, and 10th elements in the semigroup, and also the 15th and 16th elements. And with quadratic programming software, we ran a bunch of different examples for lots of different semigroups, and we always saw pictures like this. And so here's the conjecture that formed based on experiments. For any semigroup gamma, we think that for all sufficiently large capital N, there's some set of corners I where the worst one parameter subgroup always has corners at those x values for all sufficiently large N. And I can say a little bit more. The set of corners seems to have the pattern that you might have some corners that come before the conductor of gamma, but there's always going to be either 1 or 2 consecutive corners that are just a little past the conductor. And so as you raise n, you don't get something that's sort of changing forever on after that. The set of corners seems to be fixed after a certain point. Now, in mathematics, a lot of times when some property is the same for all sufficiently large degrees, we might often call that property stable, or say that something stabilizes. But that word already means something in GIT, so we had to call it something else. And so we're calling it the persistence conjecture. And like I said, it's really about sort of the set of corners that you see in the weights of the worst one parameter subgroup. Okay, so let me tell you a little bit about the status of this conjecture. We checked it again using software for all semigroups genus 1 through 12, as well as a few higher genus semigroups as well. So we've got a lot of computational evidence for this. And we've also proven this for all higher order cusps. So this is singularities of the form y squared equals x to the 2r plus 1 for any integer r. And we've got sort of an outline of a proof of this results, but we haven't written down all the details yet. So I'm calling it a conjecture today, but I'm hoping that you'll see it in a preprint in the not too distant future on the archive. Okay, so let me just mention very briefly what our approach. The first is we dropped from the quadratic programming problem that comes to us from algebraic geometry to a slightly simplified one, which amounts to replacing one entry in the vector A by a 2 instead. And then you want to show that the optimum is always greater than or equal to 2, and then it's enough to show that when n gets sufficiently large, you get at least one corner past the conductor, and then we can use that to prove all the other properties that we expect. A little bit about our methods. We've been using something called the Kanish-Kuhn-Tucker conditions. So I wanted to mention this to this audience because this is a lot of people in algebra, number theory, algebraic geometry. This is something that's bread and butter for our friends over in analysis. And so I wanted to highlight it for this audience as well. So what are these? These are a generalization of Lagrange multipliers to the situation where you have an optimization problem with some constraints given by equations and also some constraints given by inequalities. Okay. There are necessary conditions that are satisfied by a lot of optimization problems, and for many optimization problems, including the one that we're considering, where you've got, looking for the closest point between a vector and a polyhedral cone, the KKT conditions are also sufficient conditions. Okay, and so here's what I've been doing for every semigroup gamma, every set of corners I, and for any value n. You can write a matrix equation that allows you to find the stationary points on a face of your cone and all these KKT multipliers. And then when you look at what happens as n increases, you see that these matrices satisfy a recurrence relation, and you can use that to deduce properties of the solutions. Okay, and so here's our last slide. Let me tell you the answer for cusp, which is slightly surprising. Consider a higher order cusp, so y squared equals x to the 2r plus 1. The worst one parameter subgroup is always going to have a pair of consecutive corners, and j is going to be the roundup of the root of this polynomial. And I can almost give you a closed formula for it. It's almost always equal to the expression you see here, although I didn't actually prove that. What's easy to prove is that this number j is either this quantity or that plus 1. And so, like I said, it was just slightly surprising to us when we worked out this formula that you get, kind of a irrational answer, even though you start with, sort of a really reasonable set of singularities. All right, that's all. Thank you very much.